This is a pretty short section on problem-solving hints. So some hints for problem solving. First, there may be more than one answer. Second, there may be more than one method. Third, use the appropriate tools. Fourth, consider similar problems. Fifth, consider equivalent problems with simpler solutions. Sixth, approximations can be useful. Seventh, try alternative patterns of thought. And 8, do not spin your wheels. Okay? So for these examples, there was so much writing, I went ahead and typed it up for you so you didn't have to copy it down. So we're just going to talk through these. Example 1, tickets for a fundraising event were priced at $10 for children and $20 for adults. Shauna worked the first shift at the box office, selling a total of $130 worth of tickets. However, she did not keep a careful count of how many tickets she sold for children and adults. How many tickets of each type did she actually sell? Well, if they had told us how many tickets total she sold, not just the cost, then we could have done this algebraically, but she didn't. So really the only way is by trial and error. Think about if she sold just one $10 child ticket. Then she would have sold $120 worth of adult tickets. Since adult tickets were $20, divide by 20, she must have sold 6 adult tickets. So 6 adult tickets and 1 child. Thing is, this isn't the only option. I mean, if she sold 7 total tickets, then yeah, this would be the answer. But we don't know how many tickets she sold, so there could be other answers. For example, suppose she sold 3 of the $10 child tickets for a total of $30. Then she would have sold $100 worth of adult tickets, or 5 adult tickets. 3 childs and 5 adults, that also works. In fact, there's 7 possible answers to the question. And you can read through that if you want. And example 2 says Jill and Jack, I thought it was Jack and Jill, ran a 100-meter race. Jill won by 5 meters. That is, Jack had run only 95 meters when Jill crossed the finish line. They decided to race again, but this time Jill starts 5 meters behind the starting line. Assuming that both runners run at the same pace as before, who will win? Well, it seems to be obvious that they'd end up at the same time, doesn't it? That's not the case. One approach to this problem is looking at it analytically. We're not told how fast either Jill or Jack ran, so we can choose some reasonable numbers. For example, we might assume that Jill ran the 100 meters in 20 seconds. In that case, her pace was 100 divided by 20, or 5 meters per second. Because Jack would have only run 95 meters in the same 20 seconds, because he was 5 meters behind, his pace was only 4.75 meters per second. So for the second race, Jill must run 105 meters, while Jack runs 100. We predict times by dividing their respective race distances by their speeds from the first race. So 105 meters divided by 5 meters per second, that was Jill's speed, would be 21 seconds. Looks like my formatting messed up a little bit. But with Jack, 100 meters divided by his speed of 4.75 meters per second, it took him slightly bit longer, 21.05 seconds. So Jill still wins. And although the analytical method works, we can use a more intuitive and direct solution if we wanted to. In the first race, Jill runs 100 meters in the same time that Jack runs 95. Therefore, in the second race, Jill will pull even with Jack 95 meters from the starting line. In the remaining 5 meters, Jill's faster speed will allow her to pull away and win. Note how this insight avoids the calculations needed for the analytical method. Okay, so this, as I said, this section was short, just on some hints, and that's it of it.